Hello and welcome to our talk on neural precomputed radiance transfer, a collaboration between INRIA Côte d'Azur and Université College London, with myself, Gilles Rainer, Adrien Bousseau, Tobias Ritschel, and Georges Drettakis. As the title suggests, the aim of this paper was to revisit precomputed radiance transfer with deep learning tools. But where does PRT come from? The original paper was published by Sloan and colleagues in 2002. PRT is a solution to the problem of rendering global illumination in real time in situations where the compute budget is not sufficient to do full path tracing in real time. By fixing some of the scene variables, in this case the geometry and the materials, and pre-computing rendering functions for that fixed scenario, PRT allows dynamic viewpoint and environment lighting at runtime and achieves real-time global illumination. The main principle of precomputed radiance transfer is that instead of dealing with rays as in path tracing, PRT deals with functions on the spheres, so angular distributions. In particular, to shade a point in the scene, the distant dynamic environment map is projected onto the angular basis. The transfer function, which transforms the distant lighting into local incoming lighting at the given point, is looked up from the precomputations and applied. Finally, this incoming light to the point is convolved with the BRDF at the point to obtain the outgoing radiance. The efficiency of PRT lies in the fact that the transfer and convolution operations are performed in the angular basis, which means either as matrix vector products or dot products, which is really efficient. The path tracing equivalent is to brute force sample all the angular directions on the sphere and to integrate them, while PRT uses this elegant formulation to reduce the problem to a dot product in this angular space. Of course, the main approximation here is the lossy projection into the spherical basis. This is why the choice of basis has been one of the main domains of research in subsequent papers with propositions like Haar wavelets, spherical Gaussians, and so on. Other works have explored the compression algorithm, the types of light transport that PRT models, so whether it's direct, one bounce, or full global illumination, and whether some of the initial restrictions can be lifted. So, for instance, to allow deformations of objects, dynamic materials, and more general local lighting. Recently, deep learning has crept into PRT, with, for instance, CNNs being used to predict pixel-to-pixel transport coefficients, so that's to relight images, or CNNs can be used as regularizers to predict coherent transport coefficients on the deformations of the geometry, or coefficients of unstable bases like spherical Gaussians. But no one has tried to make a neural renderer in the very specific style of PRT. Instead, the main focus of neural rendering has been mostly on real-world data, for instance for free-view synthesis and relighting, where networks are able to extract information from the captured data and find correlations. More recently, deep learning has also found its way into the rendering pipeline, so here for synthetic data. Here the approximation capabilities of networks are interesting because they alleviate the heavy computational load of path tracing. So some examples of use of deep learning include to model geometry, to model materials, and finally to model the shading. Radiance regression functions famously introduced as a precursor deep learning into the rendering pipeline in 2013, a long time ago, and very recently neural radiance caching trains a neural cache on the fly in real time. Neural rendering is sort of an umbrella term for all algorithms that produce images and involve a neural network, but this neural shading is the most relevant domain of neural rendering to us. Here, networks are trained to produce shading at any scene point, given some attributes of that point. Usually those attributes come from the G buffer, and optionally some representation of the lighting. NeRF, neural radiance caching, radiance regression functions, compositional neural C representations are all examples of this specific type of neural rendering pipeline. And to obtain the highest quality rendering, those networks would typically not be trained to generalize, but trained per scene. So here, for instance, one would render a given scene under many different viewing angles and lighting conditions and train the network to reproduce those. So to learn to relight new views, the network will then basically become a compressed representation of the light transport in that particular scene. So hopefully this is starting to reveal some parallels between neural rendering, more specifically neural shading, and PRT. So there's the pre-computation of a data set, there's the compression of this pre-computed light transport, the extraction of a transport function, efficient runtime, and projecting distributions into low-dimensional descriptors. So now that I've introduced the relevant background on PRT and neural rendering, I'll describe the methodology that we used for this paper. So our goal was to explore the design space of such neural shaders with decisions inspired by PRT and grounded in light transport theory. We present 4 different architectures with increasing amounts of inductive bias and show that given a fixed neural budget, the more the network respects PRT principles, the better the quality of the result will be. So we start from the projection of the illumination into a low-dimensional descriptor. This is the neural equivalent to the projection into spherical harmonics in the original PRT paper. And to do this, we simply use a CNN encoder that takes the environment map as input and embeds it in a latent vector. Sloan and colleagues project to spherical harmonics. Our CNN learns which latent space it is projecting to. So it's a nonlinear projection to a latent space that does not have any of the orthonormality properties of spherical harmonics. But that being said, the encoding is learned, so it is specific to the scene. If, for instance, the scene has a window and light only comes into the scene through that window, the network, the encoder here, will learn to ignore any part of the environment map that is hidden by walls, for instance. So this learned encoding should be more compact and have more representational power than, for instance, general spherical harmonics. This step is very important and also subject to exploration, but we leave this part as is and assume that the CNN encodes the most information out of the environment map into a compact code. So instead we focus on the design of the runtime shading. So this is the part that we explore the most. In traditional PRT, the pre-computed data is stored in a compressed format. So to shade a point, the data needs to be decompressed to retrieve the pre-computed light transport for that given point, so it can be applied. In our neural equivalent, the network itself is the compressed data. So we would like it to learn the transport in a compressed way and apply it correctly to the given point. So to do this, we retrieve the G buffer attributes that describe the point, concatenate them to the lighting code, and let the network do the rest. So we refer to this as the simple naive baseline, since we let the network do everything implicitly internally. That means both learn the compressed light transport, learn to retrieve it for a given point, and apply it. We can go one step further by forcing the network to separate the 2 main steps of PRT. That is the lookup of the transport and the dot product with the lighting. We can achieve this by simply having one network learn the transport as a function of the point, so as a function of the position in the scene, and effectively that network will be responsible for compressing the transport in the scene, and then a second network that learns to combine the transport at a given point with the lighting to produce the final appearance. So effectively, this second network is learning the equivalent of the dot product in PRT. So this second network will receive the concatenation of the learned transport code and the learned light code. One more detail, we use layers with sinusoidal activations for the first network, since those are much better at encoding all frequency details. ReLU activations are typically biased towards low frequencies, and these siren layers have proven better compression when learning high-dimensional signals as a function of low-dimensional coordinates. So for the second network, we use ReLU layers instead, since we are concatenating 2 high-dimensional signals as inputs, which works well with ReLU but not with sines. So in the end, sine activations for the first network, ReLU for the second, works the best to encode all frequencies of light transport in the scene. So that's our second architecture, mimicking really the bare bones structure of PRT. First, the lookup of the transport function in a spatial structure, it's performed by the first network, and then the dot product with lighting. And both of these elements are learned. The second important concept in PRT is the distinction between transfer and transport. The matrices that are pre-computed describe the transfer from distant illumination to local incoming light at the point, but not the full transport, which would go all the way to outgoing radiance. The incoming radiance still needs to be convolved with the BRDF kernel to obtain the outgoing radiance. And this BRDF kernel is expressed in the same angular basis as the incoming lighting to make this operation really efficient. We take inspiration from this, but implement it in a much simpler way. So instead of directly predicting the final outgoing radiance at the pixel, we predict diffuse and specular radiance. Both of these need to be multiplied by the diffuse and specular albedos respectively, and summed together to obtain the final value. This might seem like a simple tweak, but it means that in a situation where you have a smooth shadow over a textured surface, the network only needs to learn the smooth shadow values, and the modulation with the texture happens afterwards explicitly. So the signal learned by the network is just a smooth function, which is much simpler and will be learned much better. Finally, we introduce one more design version where diffuse and specular transport are modeled entirely separately. So this is also inspired by the original PRT paper, where diffuse and specular are separated. Diffuse transfer typically works as in the form of a vector, since it is view independent. The outgoing radiance is view independent, so there's 2 dimensions fewer, while glossy transfer typically needs a matrix. Since it's view dependent, it has 2 more dimensions, and it just makes the whole transfer more complex. This also means that for the diffuse transfer, fewer spherical harmonic bases can be used, and for the glossy transfer, typically more coefficients are used. In our neural equivalent, there's no explicit frequency handling, so we just let the networks learn and overfit to the type of signal that fits best. But still, separating diffuse from specular is a good idea, since the 2 types of transport have different properties. For instance, we do not need to give the view direction as input to the diffuse track. It only needs to learn from the position, normal, and diffuse albedo, and this will force it to learn view agnostic appearance. And similar stuff for the specular track, and this just means that overall this model is much more physically based, and each of the tracks really learns its specific type of transport. So these were the 4 designs that we explore. They all correspond to enforcing different levels and principles of PRT and light transport knowledge. For a more formal derivation with analogies to PRT formulas and analogies with our learned components, we refer to the paper. So how do the 4 designs perform visually? Let's look at some close-ups from 2 scenes. So just to show the entire scenes here, these are views of the entire scene, but we only focus on the little insets. So these are decent sized scenes under illumination conditions that were not seen at training time. So let's start with the simple baseline and the path traced ground truth. As can be seen, the baseline architecture isn't terrible, but it is missing some details. The reflections on the plates are kind of blurry, and the nightstand appears to be floating over the wooden floor. This is because this naive network is entangling all the inputs and all the effects that it needs to learn. The PRT inspired design does much better, since its first MLP can learn a light independent transport descriptor for a given point, and then the second network only learns to relight a spatial code. So this improves the realism a lot more, since now the network cannot bake in reflections or shadows anymore. It actually needs to learn a more physically based representation of the transports. And then the albedo factorization allows to learn something closer to transfer than transport, so model something closer to incoming than to outgoing light. And where the first 2 designs would struggle to create a smooth shadow on the textured floor under the nightstand, this network now manages to actually produce a realistic shadow, and it doesn't look like the nightstand is floating anymore, especially the bottom right foot. And finally, the complete separation of diffuse and specular tracks allows for a much more physically based disentanglement of view-dependent effects from diffuse effects. So for instance, the reflections on the plate, which are purely specular, are now much better. And these the two last architectures achieve better quality results, but this involves a trade-off, since the improvement in quality also comes with slower runtime inference. So you can see here on the bottom right that the diffuse specular separation is a little bit slower than the albedo factorization, and there's a speed quality trade-off here and a sweet spot somewhere in the middle. And of course, the numbers confirm the observations for the errors. With each addition of physically based and PRT-based design elements into the architectures, the error becomes lower and improves. One more thing about the timings. We use the slowest of our timings, so the diffuse specular separation, to adjust the budget that we give to all our comparisons. So all the real-time methods that we compare against have slower rendering times than our slowest design. So for instance, with real-time path tracing, this allows us a budget of 5 samples per pixel. And on a more simple scene like this, the results on individual frames are decent, but the temporal inconsistency of the denoising is really noticeable. And if we go to a more complex scene, it turns out that 5 samples per pixel is just not enough to recover sufficient information about the light transport. It's either very noisy, or if you use denoising, very temporally inconsistent. We also compare to the recent neural radiance cache, which is also a neural shader, and it works by path tracing the first bounces and then querying the neural cache at the deeper bounces, which is also trained in real time at the same time. So as you can see on the left, the cache does a good job of overfitting to the scene very quickly, but when the camera and the light conditions change, it's always lagging a bit behind. And this is even more noticeable in complex scenes like this, where the cache basically introduces undesired bias into the global illumination. And also, since it relies on real-time path tracing for the first bounces, the noise from the insufficient number of samples per pixel is also really noticeable. Finally, we also show what traditional PRT would look like here for a fixed camera. So this is a simplified implementation that we did. The main conclusion here is basically that even with 5 spherical harmonic bands, so that's 25 coefficients, spherical harmonics tend to cut off the high frequency angular signals. So this is visible on the mirror, for example. Our learned light and transport codes are capable of representing high frequency signals much more accurately. Also, there's a speed memory trade-off here. PRT only requires a dot or a matrix product to do the shading, plus the lookup, so it will be faster than evaluating a full network. That said, the precomputed data is essentially represented in our network, which is the compressed version of it, so we don't need to perform any lookups in memory. In PRT, storing coefficients at every point or at every pixel here, as we did, quickly becomes prohibitive, so it uses a lot of memory. In conclusion, we proposed a lightweight neural rendering method for a fixed scene with fixed objects and fixed materials and dynamic environment lighting. But most importantly, this work was about analyzing how to inject knowledge from PRT methods into neural rendering architectures to improve the quality and essentially get the most out of a fixed neural budget. Our work was focused on keeping the neural budget, so the training, the dataset, the network size, and so on, constant, and improving the quality via tweaks in the architecture. But this is only one direction in a wide design space. There are many other directions to explore. So active exploration by Drettakis and colleagues, for instance, explores how to optimize the data generation during training to get the most out of their neural renderer by basically training it on the more challenging parts of the scene, which is inferred during the training online. Instant NGP explores the memory versus computation trade-off, for example, for neural radiance fields. So rather than having the network learn the spatial lookup and the radiance, they store some codes in an optimized spatial structure. That way the lookup and compression operation is taken out of the network, which can be much smaller and train much quicker. It would also be interesting to investigate a little bit more the encoding of the illumination, for instance, maybe through spherical CNNs. And finally, the holy grail would be to generalize all of this to unseen scenes or materials, to make the entire scene arbitrary, for instance, by learning a local scene code in the same way that our network learns a transport or a light code. Thank you for your attention.